Hello, welcome to the deep space. Every time you look up at the starry sky, do you ever wonder about our Milky Way galaxy? How exactly was it born? Just how vast is it? Why did only us humans come to exist here? Now, join me as we explore this boundless cosmic home. I'd be incredibly grateful if you could subscribe to my channel. Give the video a thumbs up. Not only does it help the algorithm recommend more cosmic content to you, but it's also a huge support for me. It helps me create more amazing journeys across the universe. I'm also curious to know where you are and what time it is right now. Please leave your location and time in the comments below. Now gently close your eyes, or let your gaze rest softly upon the distant horizon. Let us momentarily forget the daily trivialities and clamor, and together contemplate an ancient story about us all. This story isn't written on paper, but etched into every atom of the universe. Modern astronomy and physics reveal a profound and magnificent truth. All matter in the universe shares a common origin. This includes you and me. It includes this blue planet beneath our feet, and those distant, twinkling stars. At the primordial moment 13.8 billion years ago, the universe began expanding from an unimaginably hot and dense state. This is what we call the Big Bang. In the first few minutes, the universe was a fiery ocean of fundamental particles. As it rapidly expanded and cooled, the simplest elements began to form, primarily hydrogen and helium, along with trace amounts of lithium. At that time, the universe contained no carbon, no oxygen, no iron, and certainly none of the complex elements essential for life. The cosmos was a simple, primordial sea of elements. The first generation of stars ignited within these primordial gas clouds. They were massive and fiery, their lives brief yet brilliant. Deep within the nuclear furnaces of these stars, nuclear fusion reactions commenced their grand work of element creation. Hydrogen fused into helium. Helium fused further into heavier elements like carbon and oxygen. Yet many heavy elements vital to life, such as iron and gold, required even more extreme environments to forge. When massive stars reached the end of their lives, they met their demise in supernova explosions, the most spectacular fireworks in the cosmos. Under such extreme energy and pressure, heavier elements were synthesized and scattered across interstellar space. Additionally, events like neutron star mergers serve as major cosmic factories for producing heavy elements like gold. These materials, forged by stars and scattered into space, mix with primordial gas to become the raw material for birthing new generations of stars and planets. Our sun is such a second or third generation star, born approximately 4.6 billion years ago, from a molecular cloud containing remnants of earlier stars. The primordial nebula that formed our solar system, already rich in life-essential elements like oxygen, carbon, nitrogen, and iron. Thus, every breath of oxygen you inhale was created by a massive star that died before the sun was born. The iron atoms in your blood that carry oxygen likely originated from an ancient supernova explosion. The calcium in your bones, the phosphorus in your DNA, the sodium and potassium within your body, all these essential elements sustaining life, were all forged in the distant past, deep within the heart of some dying star. After billions of years of cosmic cycles, this stardust ultimately gathered here to form our Earth, and to form you who are listening at this very moment. From this perspective, we are not merely living within the universe. We are the universe itself. We are a way for the universe to know itself. We are a fleeting and precious gathering of stellar matter, bearing the ancient history of the cosmos, and contemplating its boundless future. This realization lays the foundation for our journey through the Milky Way, For what we are about to explore is not merely a distant external celestial system. We are exploring our most ancient and grandest home, exploring our own origins and destiny. Now, carrying this awareness of interconnectedness, let us drift deeper into our galactic home. When we gaze at the night sky from Earth and see that hazy band stretching across the heavens, what we behold is the inner edge of the Milky Way's disk. This luminous band, known as the Milky Way, is the view we see when observing our own galaxy from within. It took astronomers centuries of effort to gradually piece together the full picture of this immense stellar system we inhabit. The Milky Way is a classic barred spiral galaxy. This means its center isn't a simple spherical nucleus, but a short, bar-shaped structure composed of stars. This massive stellar bar spans approximately 27,000 light-years. It rotates slowly, stirring the material at the galaxy's core and influencing the evolution of the entire galactic structure. From a structural perspective, the Milky Way can be clearly divided into several major components, which collectively form this magnificent cosmic island. The most striking feature is the galactic disk, a flat, disc-shaped structure composed of stellar gas and dust. The Milky Way band we observe is precisely the projection of this disk onto the sky. The galactic disk is the most active and vibrant region of the Milky Way. Here, young stars cluster, bright nebulae shine, and molecular clouds incubate new stellar births. The galactic disk spans approximately 100,000 light-years in diameter. This means that even traveling at the speed of light, it would take 100,000 years to traverse from one end of the Milky Way to the other. The thickness of the galactic disk is not uniform. It is thicker in the central region and thinner in the outer regions. Its average thickness is about 1,000 light-years. Our solar system resides within this disk. At the disk center lies the Milky Way's most mysterious and densest region, the galactic center. Here, stars are packed exceptionally tightly, with millions clustered within a cubic parsec of space. By comparison, the star density near our Sun is far sparser. The galactic center is obscured by vast clouds of interstellar dust and gas, blocking our visible light view, making it impossible to glimpse its true form directly with optical telescopes. However, through observations in the infrared and radio wavelengths, we are able to penetrate this thick veil. At the core of the galactic center lies a powerful radio source, named Sagittarius A star. All evidence points to one conclusion: a supermassive black hole exists there, with a mass equivalent to 4.3 million suns. Though this black hole itself emits no light, it dominates the orbits of central stars through its immense gravitational pull and accretes surrounding matter. Before falling into the black hole, this matter is heated to extremely high temperatures, emitting intense radiation. Beyond the galactic disk and bulge lies a vast, nearly spherical structure, the galactic halo. The halo extends far beyond the visible edge of the disk, potentially spanning hundreds of thousands of light-years in diameter. The matter within the halo is extremely sparse, primarily consisting of ancient globular clusters and vast numbers of sparsely distributed, aged stars. These stars typically orbit independently, along elongated elliptical paths around the galactic center. Scattered throughout the halo are remnants of dwarf galaxies torn apart by tidal forces. The stellar streams they form resemble vast ribbons, wrapped around the Milky Way, silent witnesses to its history of consumption. But most importantly, the galactic halo is the primary reservoir of the Milky Way's dark matter. This invisible substance constitutes the majority of the galaxy's mass, providing the additional gravitational force required to bind the entire galaxy together. Without dark matter, the Milky Way would disintegrate under its own high-speed rotation. Viewed from above the galactic disk, the Milky Way's most captivating feature is its massive spiral arms. These arms are not composed of fixed stars, but patterns created as density waves propagate across the galactic disk. Imagine it as a traffic jam zone, where cars continuously enter the congested area, slowing down and increasing density within it, before exiting and continuing their journey. While the jam itself slowly moves along the road, stars and gas clouds behave similarly, entering the spiral arm region, compressed by gravity, triggering new star formation, then departing the arm as they orbit. Thus, spiral arms are the brightest, most dazzling regions in a galaxy, because they host numerous short-lived, luminous, massive blue stars. Their light illuminates the surrounding gas clouds, outlining the contours of the spiral arms. Regarding exactly how many major spiral arms the Milky Way possesses, astronomers continue to study this question. Traditional models propose 4 major spiral arms. They are the Perseus arm, the Quadrans Maceae arm, the Sagittarius arm, and the Scutum Carina arm. However, recent observational data suggests the Milky Way's structure may be more complex. Perhaps only 2 major spiral arms are continuous and prominent, namely the Perseus arm and the Scutum Carina arm, while the others may represent minor branches or local features. These spiral arms extend outward from the central bar of the galaxy, like vast cosmic whirlpools, unfolding across the galactic disk. Now let us turn our gaze back to our own position. The solar system does not lie on any of the major spiral arms. Instead, it resides within a relatively minor structure, the Orion arm, sometimes referred to as the local arm or Orion spur. This branch lies between the Perseus and Sagittarius arms, can be viewed as a bridge connecting the 2 major spiral arms. The Orion arm spans approximately 10,000 light-years. It is not a complete spiral arm, but rather a local spiral fragment composed of stellar gas and dust. Many of the bright stars and nebulae we recognize, such as the Great Orion Nebula, are situated within this local arm. This provides an excellent laboratory for observing star formation. On a cosmic scale, our location is actually quite ordinary. We are positioned approximately 27,000 light-years from the galactic center, very close to the Milky Way's common rotation plane. At this radius, the orbital velocity of stars around the galactic center roughly matches the rotational speed of the spiral arm pattern. This may be a fortunate circumstance, preventing us from frequently traversing high-density, high-radiation regions of the spiral arms, thus providing a relatively tranquil cosmic environment for the long-term stable evolution of life on Earth. Finally, let us use some concrete figures to grasp the breathtaking scale of the Milky Way. The visible matter mass of the Milky Way is roughly equivalent to 100 billion solar masses. This encompasses approximately 100 to 400 billion stars. The uncertainty in this range stems from imprecise estimates of low-mass, dim red dwarf stars, and the obstruction of our observations by interstellar dust. Imagine, if every star in the Milky Way were a grain of sand, the entire galaxy's stars would fill a large swimming pool, and our Sun is just one ordinary grain among these tens of trillions of grains. Traveling at the speed of light from one end of the Milky Way to the other would take 100,000 years. Yet our spacecraft traversed the distance between Earth and the Moon in just over 1 second. This contrast in scale deeply reminds us of our own insignificance and the vastness of the universe. Yet it is precisely this tiny speck that can contemplate, explore, and appreciate this magnificent whole. This in itself is a miracle, Understanding the structure and scale of this magnificent spiral we inhabit is the foundation for comprehending all the stories unfolding within it. From the birth of stars to their demise, from the gravitational pull of dark matter to the reign of central black holes, all these dramas unfold upon this vast stage spanning 100,000 light-years in diameter. And we stand upon this stage. Before the 20th century, astronomers believed luminous celestial bodies, stars, nebulae, and galaxies constituted the bulk of the material universe. Yet a series of sophisticated observations and calculations radically overturned this understanding, leading us to discover the dominant component of the cosmos, a mysterious substance we cannot see or touch. Dark matter, one of the most crucial clues in this story, came from measuring the rotational speeds of galaxies. According to Newton's law of universal gravitation, a rotating system like the Milky Way should exhibit decreasing orbital speeds for outer celestial bodies as they move farther from the center. Much like planets in our solar system, Mercury orbits the Sun much faster than Neptune, because the gravitational pull from the center weakens with distance. When astronomers attempted to plot the Milky Way's rotation curve, a graph showing the orbital speeds of stars and gas relative to their distance from the galactic center, they were astonished to discover that across most regions far from the galactic core, these speeds did not decrease as expected, but instead maintained a nearly constant high value. This implies that beyond the visible luminous disk of the Milky Way, there exists a substantial amount of additional mass we cannot see. This mass generates stronger gravitational forces that bind the outer stars and gas into high-speed orbits, preventing the galaxy from flying apart due to excessive rotation. If the Milky Way contained only the stars and gas we can observe, its gravity would be far too weak to sustain its current rotational speed. The galaxy should have disintegrated long ago. This mystery of the rotation curve stands as one of the strongest pieces of evidence for the existence of dark matter. It reveals that visible matter constitutes merely the tip of the iceberg. To explain the observed galactic dynamics, astronomers proposed the concept of a dark matter halo. They posit that the Milky Way, along with all similar galaxies, is embedded within a vast, roughly spherical dark matter halo. This halo extends far beyond the visible boundaries of the Milky Way, with a diameter potentially exceeding 1 million light-years, functioning like an invisible, colossal container, enveloping the entire luminous galaxy. According to the most precise current estimates, dark matter constitutes approximately 85% of the Milky Way's total mass, while everything familiar to us, all stars, planets, nebulae, and interstellar gas, combined account for only the remaining 15%. This ratio implies we inhabit a universe dominated by invisible matter. The dazzling starry sky we observe is merely a shimmering surface floating atop a profound ocean of dark matter. Dark matter not only governs the rotational behavior of entire galaxies, but also plays a decisive role in the formation and evolution of cosmic structures. In the early universe, it was precisely dark matter, due to its non-interaction with light. It was the first to coalesce under gravitational forces, forming the initial network of gravitational potential wells in the cosmos. This gravitational skeleton, composed of dark matter, provided the space and conditions for subsequent ordinary matter accumulation. Gas and dust were drawn to these regions of higher dark matter density, gradually cooling and condensing, ultimately igniting the first generation of stars, and coalescing into the galaxies we observe today. It can be said that without the initial gravitational framework provided by dark matter, grand galaxies like the Milky Way could never have formed, or their structures would be vastly different from what we observe today. Dark matter is the true architect and engineer of this cosmic edifice. So what exactly is dark matter made of? This remains one of the most profound and pressing mysteries at the forefront of contemporary physics. We know it is not any conventional matter we recognize. It is not the protons, neutrons, or electrons that compose stars and planets, because it neither emits, reflects, nor absorbs light. Nor is it conventional black holes or dim celestial bodies, as observations through techniques like microlensing have ruled out the presence of such objects on a large scale. Current mainstream theories suggest dark matter is a novel fundamental particle beyond the standard model of particle physics. Among the most prominent candidates is the weakly interacting massive particle, abbreviated as WIMP. As its name suggests, this hypothetical particle interacts with ordinary matter only through the weak nuclear force and gravity. Its mass may be tens to hundreds of times that of a proton. These particles were thermodynamically produced in the early universe. Their residual abundance precisely explains the observed dark matter density. This coincidence is known as the WIMP miracle, prompting scientists worldwide to construct multiple highly sensitive underground detectors to capture the extremely rare collisions between WIMPs and ordinary atomic nuclei. Yet, despite decades of relentless searching, these experiments have yet to yield conclusive evidence. Another strong contender is the axion, an extremely lightweight hypothetical particle, proposed to resolve the charge parity conservation problem in strong interactions. Axions exhibit a weak coupling with photons in electromagnetic fields, producing detectable signals. Currently, multiple experiments are utilizing precision resonant cavities to search for this ultralight dark matter particle both in the cosmos and in laboratories. Additionally, several other intriguing hypotheses exist, such as sterile neutrinos, or modifications to gravitational theory, suggesting that what we perceive as dark matter effects may actually be manifestations of gravitational laws requiring correction on galactic scales. However, the latter theory faces significant challenges in explaining observations of the large-scale structure of the universe. The quest to uncover the nature of dark matter is a grand journey spanning astrophysics, particle physics, and cosmology. Whether through underground direct detection experiments, indirect production via the Large Hadron Collider, or observing signals from dark matter particle annihilation using space telescopes, scientists worldwide are approaching the core of this enigma from every angle. Understanding dark matter is not merely the key to unlocking the mystery of galactic rotation, but a crucial step in comprehending the composition of cosmic matter and fundamental physical laws. It represents the frontier of human knowledge and reminds us that countless unknowns in the universe await discovery. When we gaze upon the stars once more and realize our Milky Way is enveloped by a vast, profound dark matter halo, what we feel may transcend mere cosmic vastness and touch upon profound mystery. This invisible framework silently sustains the myriad stars we behold, shaping our cosmic home. The mission to unveil its veiled secrets inspires generation after generation of explorers to pursue the cosmic truths hidden in darkness. When we gaze upon the night sky and behold that seemingly eternal band of Milky Way light, it's easy to fall into the illusion that our galaxy is a stable, timeless structure. Yet modern astronomy reveals a starkly different story. Our Milky Way is a vibrant, dynamic system with a turbulent past and a future heading toward dramatic upheaval. This shift in perception stems from our deeper understanding of the cosmos. It stems from the rapid advancement of observational technology, and the continuous refinement of theoretical models. Understanding the formation and evolution of galaxies stands as one of the core challenges in contemporary astrophysics. The currently widely accepted model is the hierarchical formation model. This model depicts the cosmic structure as gradually building from small to large. In the first few 100 million years after the universe's birth, matter began to coalesce under the gravitational framework provided by dark matter. The first structures to form were small, faint dwarf galaxies and stellar clusters. These primordial building blocks of the cosmos, driven by gravity, attracted each other, collided, and eventually merged. This process resembled a cosmic construction project spanning billions of years. Smaller structures coalesced into larger ones. Galaxies gradually grew through continuous mergers and accretion. Let us turn our gaze to the infancy of the universe. When its age was less than 1 billion years, primordial gas began cooling and condensing within dark matter halos. The first generation of stars ignited within these primordial gas clouds. Their intense ultraviolet radiation began ionizing the surrounding neutral hydrogen. This process, known as the reionization era, created the conditions for further cosmic structure formation. The dwarf galaxies formed during this period, though individually small, became the building blocks for larger galaxies. Over time, these smaller galaxies began approaching each other under the influence of gravity, moving along filaments of dark matter, much like water converging along river channels. When two galaxies encounter each other, they do not collide directly like solids, but undergo a complex dynamical process, in which stellar orbits are redistributed. Gas clouds collide and compress, triggering new star formation. These galaxy-scale merger events significantly alter a galaxy's appearance and internal structure. The Milky Way is no gentle giant. It possesses a voracious appetite, continuing to devour dwarf galaxies orbiting it to this day. By analyzing stellar positions and motions, particularly using precise data from the European Space Agency's Gaia mission, in the halo of our Milky Way, have uncovered numerous remnants of mergers from different generations. These remnants, akin to archaeological strata, chronicle the galaxy's lengthy history of devouring others. Among the most significant discoveries is the merger event known as Gaia Enceladus, sometimes referred to as the Milky Way's last major merger. This event occurred approximately 8 to 10 billion years ago. A large satellite galaxy named Gaia Enceladus underwent a violent merger with the primordial Milky Way of that era. This satellite galaxy may have possessed a mass equivalent to 1/4 of the Milky Way. This collision profoundly reshaped the Milky Way's structure, potentially facilitating the formation of its central bar and thick disk, while flinging hundreds of millions of stars into the galactic halo. By analyzing high-precision data from the Gaia spacecraft, astronomers have identified groups of stars sharing a common origin. These stars exhibit similar orbital motions and chemical compositions. As if possessing identical DNA, kinematic analysis reveals distinct group characteristics. Their orbits display high eccentricities, markedly different from those of the Milky Way's native stars. Chemically, these stars typically possess lower metallicity, reflecting their formation in different environments. Beyond this major merger, the Milky Way continuously devours its current satellite galaxies, with the most famous example being the Sagittarius Dwarf Elliptical Galaxy, SDEA. This small galaxy is being torn apart by the Milky Way's powerful tidal forces. Since its discovery in 1994, astronomers have tracked its fate. Observations reveal the galaxy has been stretched into a long stream of stars, circling the Milky Way multiple times, like a broken pearl necklace. scattered across the Milky Way's halo. Another notable satellite galaxy is the Large Magellanic Cloud. This relatively large companion galaxy is exerting gravitational influence on the Milky Way's outer structure. Recent research indicates the gravitational pull of the Large Magellanic Cloud is stretching the Milky Way's dark matter halo, causing slight warping in the galactic disk. This interaction may trigger new star formation activity in the future. Each such merger event brings new stars and gas to the Milky Way, altering its dynamical structure and sparking fresh waves of star formation. When gas-rich dwarf galaxies fall into the Milky Way, the fresh fuel they bring can reignite star formation. Particularly in the central regions of the Milky Way, this gas accumulates toward the center, potentially activating dormant supermassive black holes. The history of the Milky Way is a chronicle stitched together from the remnants of countless dwarf galaxies. Every star above our heads may have a completely different origin story. Some stars are the Milky Way's natives, formed here from the very beginning. Others are immigrants, originating from satellite galaxies devoured by the Milky Way. By studying the chemical composition and motion characteristics of these stars, astronomers can reconstruct the Milky Way's formation history, much like archaeologists reconstruct ancient civilizations through artifacts. Yet this gravitational feast is far from over. The Milky Way's future has long been predetermined by gravity, and will be co-written with our neighbor, the Andromeda Galaxy. Andromeda is the largest galaxy in the local group, more majestic than our own Milky Way. On clear nights, we can glimpse a faint spindle-shaped glow in the direction of Andromeda. That is this colossal spiral galaxy. Through precise observations by the Hubble Space Telescope, astronomers have determined that Andromeda is approaching us at approximately 110 kilometers per second. And this velocity continues to accelerate under gravitational influence. The gravitational interaction between the two galaxies is now detectable even by the most sophisticated instruments. This mutual attraction has been ongoing for billions of years. In roughly 3 to 4 billion years, the Milky Way and Andromeda will make their first close encounter. This will not be a simple brush past, but a slow-motion dance spanning billions of years. During the initial approach phase, the relative velocity between the two galaxies will reach hundreds of kilometers per second. However, due to their immense size, the actual timescale of this process will be measured in hundreds of millions of years. In this grand cosmic dance, the gravitational fields of both galaxies will interact violently. Tidal forces will stretch and distort the galaxy's shapes, forming long streams of stars and tidal tails. These structures may extend over hundreds of thousands of light-years, creating breathtaking sights in the night sky, because the space between stars within a galaxy is extremely sparse. The probability of two stars colliding directly is minuscule. Thus, for the vast majority of stellar systems within the galaxies, this will not be a catastrophic event. Yet, the gravitational disturbances will be profound. Close encounters between stars may alter their orbits. Some stars could be flung to the outer reaches of the galaxies, or even escape their gravitational bonds entirely, becoming wanderers in interstellar space. Planetary system orbits may also be affected, particularly in the central regions of the galaxies, where stellar density is higher and gravitational perturbations are more intense. After the initial crossing of the two galaxies, they will decelerate due to gravitational tugging and be drawn back toward each other. After several such oscillations and crossings, they will eventually dissipate sufficient kinetic energy and merge into a new, larger galaxy. This merger process is expected to be completed approximately 4.5 to 6 billion years from now. Astronomers refer to the merged product of these two spiral galaxies as Milkometa, meaning the Milky Way Andromeda galaxy. Milkometa will likely become a massive elliptical galaxy, no longer possessing the distinct spiral arm structures of the Milky Way or Andromeda, but rather a more spherical collection of stars. During the merger process, gas clouds within both galaxies will be violently compressed, triggering an unprecedented stellar formation explosion, known as a starburst. At that time, hundreds of millions of new stars will be born in a short period, illuminating the newborn galaxy. Most of these newborn stars are massive stars, with short lifespans but extraordinary brightness, making the entire galaxy exceptionally luminous in the ultraviolet spectrum. However, this celestial feast rapidly depletes the galaxy's gas reserves, causing it to gradually fade into silence over eons. Stellar formation activity will cease, leaving only longer-lived, low-mass stars to continue shining. For our solar system, the probability of surviving this cosmic-scale event is quite high, yet our sky's appearance will undergo a complete transformation. During the first close encounter, the Andromeda galaxy will become immense in the night sky, no longer a faint smudge of light, but a dazzling band of light spanning the entire celestial dome. As the merger progresses, the familiar Milky Way arch will gradually twist and vanish, replaced by a chaotic, brilliant new starry sky. Computer simulations indicate the solar system may be ejected to a position farther from the new galaxy's center, or may migrate inward under gravitational perturbations. Regardless, Earth's night sky will stage an unprecedented light show, lasting billions of years. If observers remain on Earth by then, they will witness one of the most spectacular sights in the cosmos. The dynamic evolutionary history of the Milky Way teaches us that nothing in the universe remains static. From the initial mergers of tiny structures, to the formation of today's majestic spiral, and future fusion with neighbors, galactic life follows an unending cycle. Destruction and creation, death and rebirth, are intricately woven on cosmic scales. We inhabit a relatively tranquil phase of the Milky Way's existence that allows our very existence and contemplation of its past and future. This period of calm provides the stable environment, enabling life to emerge and evolve. The next time we gaze upon the night sky, we will see not merely a static band of light, but a dynamic, living, and ever-changing cosmic home. Galactic evolution also influences the formation and evolution of planetary systems. During galaxy mergers, intense radiation environments may pose challenges to the emergence of life, yet simultaneously provide raw materials for the formation of new generations of stars and planetary systems. Heavy elements in the universe accumulate through such cycles, creating conditions for the formation of rocky planets and the emergence of life. The Milky Way's future extends beyond its merger with the Andromeda galaxy. The entire local group of galaxies undergoes similar evolutionary processes. Billions of years hence, all galaxies within the local group may coalesce into a colossal elliptical galaxy. This galaxy will contain hundreds of billions of stars, becoming an isolated island in the cosmos. During this process, intergalactic gas may be heated to millions of degrees, emitting intense X-ray radiation. Star formation will gradually cease. The galaxy will enter its senescent phase. Ultimately, when the last star fades, the galaxy will become a dark graveyard. But this will occur billions of years from now. We now inhabit the golden age of cosmic evolution. We can observe active star formation. We can study galaxy interactions. We can unravel the mysteries of cosmic structure formation. This is a unique and precious era. When we contemplate the evolution of the Milky Way, We are not merely exploring a scientific question, but also seeking our place in the cosmos. Our existence is intimately linked to the galaxy's evolutionary history. Every atom in our bodies was forged and recycled through similar cosmic processes. The dynamic nature of the Milky Way reminds us that change is the eternal theme of the universe. Yet within this change lie beautiful patterns and regularities. These laws render the cosmos comprehensible and make the existence of life possible. The next time you gaze upon the night sky, remember that what you see is not merely a static image, but an epic story spanning billions of years and continuing for billions more. Each of us is a part of this narrative, witnessing the eternal dance of the universe. Within the spiral arms and disk of our Milky Way galaxy lies a substance that appears empty yet is critically important: the interstellar medium. It is the sum total of matter within the vast spaces between stars, though its density is far lower than the best vacuum achievable on Earth. Its existence is fundamental to the birth of stars. The interstellar medium is not uniformly distributed, but a complex mixture of gas and dust. Gas constitutes the overwhelming majority of its mass, approximately 99%, though dust accounts for only a tiny fraction of the mass, plays an indispensable role in star formation. Interstellar gas is primarily composed of hydrogen and helium, the two most primordial and abundant elements in the universe. Hydrogen can exist in atomic, ionic, or molecular states, depending on the temperature and density of its environment. Beyond hydrogen and helium, interstellar gas contains trace amounts of heavier elements, collectively termed metals. Though scarce in quantity, these elements are crucial building blocks for planets and life, acting as the universe's seasoning that enriches the possibilities for forming stellar and planetary systems. Interstellar dust, however, is a more complex matter. These are minute solid particles composed of silicate and carbonaceous grains, along with ice crystals. Their size is typically only on the order of micrometers. Despite their small size, these dust particles effectively block and scatter starlight, especially in the visible light spectrum. They form the dark nebulae of the cosmos, carving out dark crevices and contours along the Milky Way's luminous band. Dust also plays a crucial role as a surface catalyst, facilitating the formation of simple molecules like molecular hydrogen, and condensing volatiles such as water ice and carbon monoxide onto its own surface. These dust particles encased in ice layers will become the core building blocks of future planets. In specific regions of the Milky Way, the interstellar medium aggregates into vast, relatively dense clouds. The largest and densest of these are called giant molecular clouds. They rank among the largest scale structures in the Milky Way and serve as the primary birthplaces for stars. A typical giant molecular cloud can possess a mass ranging from 100,000 to several million times that of the Sun, or even greater. Its scale can extend to hundreds of light years. If our solar system were placed within such a cloud, it would be equivalent to a single drop of water in the ocean. The internal structure of giant molecular clouds is extremely complex. They are not uniform spheres, but dynamic systems filled with clumps, filamentary structures, and voids. Within these clouds, density and temperature distributions are highly inhomogeneous. Numerous smaller, denser regions exist, known as dense cores. These dense cores are the direct cradles of star formation. Giant molecular clouds are extremely cold, with internal temperatures typically ranging from 10 to 20 Kelvin, approximately minus 260 degrees Celsius. At such low temperatures, the thermal motion of gas molecules slows considerably, allowing gravity to overcome gas pressure and begin dominating the motion of matter. Despite their immense mass, giant molecular clouds exist in a delicate equilibrium. Internal gas pressure, magnetic field support, and turbulent motion counterbalance inward gravitational forces, maintaining the cloud's macroscopic stability. Yet this equilibrium is extremely fragile. When an external trigger mechanism appears, the balance is shattered. The grand drama of star formation unfolds. Such triggers may originate from various cosmic events. The shockwave from a nearby massive star's supernova explosion, a density wave compression in a galactic spiral arm, or the collision of another giant molecular cloud. Regardless of the specific trigger, the outcome is always a significant increase in density within a specific region of the cloud, allowing gravity to gain dominance in that area. This dense region then begins to collapse in on itself, marking the first step in the star formation process, the emergence of gravitational instability. As the dense core undergoes gravitational collapse, its central density and temperature steadily rise. Gravitational energy is converted into thermal energy. At this stage, the forming celestial body is termed a protostar. During the protostellar phase, the central object has not yet initiated thermonuclear reactions. Its luminosity primarily stems from energy released by gravitational collapse, and the collision heat generated as material falls toward the center. The protostar is surrounded by a disk that continues to accrete matter. This disk is known as a protoplanetary disk, as it will eventually give birth to planets. The protoplanetary disk is an inevitable consequence of angular momentum conservation. The initial slight rotation of the cloud is dramatically amplified during the collapse process. This rotation prevents material from falling directly into the center, forming a rotating disk-like structure. Matter flows through this disk and eventually falls onto the central protostar. This process may last from hundreds of thousands to millions of years. For a star similar to the Sun, when the protostar's core temperature rises sufficiently to ignite deuterium fusion, it enters the pre-main sequence phase. Deuterium is a heavier isotope of hydrogen and undergoes nuclear fusion more readily than ordinary hydrogen. Although this phase contributes some energy, the star's primary energy source remains its ongoing gravitational contraction, rather than stable hydrogen burning in the core. As the pre-main sequence star continues to contract, its core temperature eventually reaches the critical threshold of 10 million Kelvin. At this point, the proton-proton chain reaction, or CNO cycle, is formally ignited. Hydrogen nuclei in the core begin fusing into helium nuclei, releasing immense energy. In this moment, a true star is born, the outward radiation pressure generated by nuclear reactions achieves a precise equilibrium with inward gravitational forces. The star enters the longest and most stable phase of its life, the main sequence phase. Our Sun is currently in this phase, having burned steadily for 4.6 billion years, and will continue burning for approximately 5 billion more years. Stars rarely form in isolation. They often arrive in groups, within giant molecular clouds. Turbulence and gravity. Collapse usually doesn't occur at a single isolated point, but happens almost simultaneously across multiple dense cores throughout the cloud. This leads stars to form in clusters, giving birth to what are called star clusters. Star clusters are primarily divided into two types: open clusters and globular clusters. Young open clusters typically contain hundreds to thousands of stars, loosely gathered together, ranging in age from millions to billions of years. These clusters serve as ideal laboratories for studying stellar evolution, since all stars within them were born nearly simultaneously from the same cloud of gas, sharing identical initial chemical compositions. yet differing only in mass. The most famous example is the Pleiades, also known as the Seven Sisters. It is a young open cluster visible to the naked eye. However, stellar bonds within clusters are not eternal. After forming, clusters orbit the galactic center. During this journey, they experience the tidal forces of the Milky Way, along with perturbations from other molecular clouds and stellar gravitational fields. These external forces gradually strip away the outer stars of the cluster, like a ball of yarn slowly unraveling. Additionally, gravitational interactions among stars within the cluster can eject higher energy stars. This process, lasting millions to billions of years, ultimately leads to the complete dissolution of most open clusters. Their constituent stars merge into the Milky Way's ordinary stellar field, becoming the isolated stars we observe in the galactic disk. Our Sun most likely formed approximately 4.6 billion years ago, within such a now-dissolved open cluster. Its siblings are now scattered across the far corners of the Milky Way, perhaps silently watching us from afar, yet unrecognizable due to the vast distances separating us. By tracing stellar trajectories and chemical signatures, astronomers are searching the Milky Way for the Sun's lost siblings. This cosmic quest spans billions of years. The birth of stars from molecular clouds is a grand cosmic poem woven by gravity and pressure, magnetic fields, and turbulence. A grand symphony composed by gravity, pressure, magnetic fields, and turbulence. It begins in the coldest, darkest corners of the cosmos, yet culminates in a blaze of fiery light. Each stellar birth does more than merely light a cosmic lamp. It sows the first seeds for the future formation of planetary systems and the emergence of life itself. Every heavy atom within our bodies was forged in such stellar nurseries. We share the deepest kinship with these distant stellar nurseries. When we gaze once more at the night sky and behold those luminous points of light, we know each one has journeyed through such a dark yet hope-filled childhood. And now, deep within some dark nebula of the Milky Way, new stars are quietly taking shape in gravity's embrace, preparing to enact a fresh chapter in the saga of light. The key to understanding a star's entire evolutionary journey lies in a remarkable chart called the Hertzsprung-Russell diagram. It plots spectral types along the horizontal axis and stellar luminosities along the vertical axis. When we plot thousands upon thousands of stars on this diagram, they do not scatter haphazardly, but instead reveal distinct sequences and regions, developed independently by astronomers Ignert Hertzsprung and Henry Norris Russell. This diagram unveils the intrinsic physical laws governing stars. In the lower right quadrant of the Hertzsprung-Russell diagram reside cooler, more massive red giants and red supergiants. In the upper left are extremely hot, extremely luminous blue supergiants. A narrow band stretching from upper left to lower right concentrates the vast majority of stars. This is the main sequence. 90% of a star's lifetime is spent on the main sequence, in a state of hydrostatic and thermal equilibrium. Stable hydrogen fusion reactions in the core provide sustained energy. A star's position on the main sequence is almost entirely determined by its mass. Stars with greater mass exhibit higher core temperatures and pressures, and more intense nuclear fusion reactions. Consequently, they are hotter and brighter, but also consume their fuel more rapidly and have shorter lifespans. A blue supergiant with 20 times the Sun's mass may only shine for a few million years, while a red dwarf with only half the Sun's mass can burn steadily for trillions of years, far longer than the current age of the universe. Our Sun is a typical G-type main sequence star, located in the middle section of the main sequence on the Hertzsprung-Russell diagram. It has been burning steadily for 4.6 billion years, currently in the most vibrant middle age of its life. When a star's core hydrogen fuel gradually depletes, the equilibrium of its life is disrupted. It begins entering a turbulent late stage. Its evolutionary path diverges significantly, and at this crossroads of divergence, mass remains the decisive factor. Let us first trace the fate of a low-mass star similar to our Sun. The destiny of such stars is relatively peaceful, yet equally imbued with cosmic poetry. When hydrogen in the Sun's core is exhausted, forming a core of inert helium, hydrogen fusion does not cease immediately, but shifts to continue in a thin shell layer surrounding the helium core. The additional energy generated by shell hydrogen burning causes the star's outer layers to expand dramatically. Its radius can increase hundreds of times. Surface temperature consequently drops. Its color reddens. The Sun will evolve into a red giant. At that point, its edge will engulf the orbits of Mercury and Venus. It will likely also swallow Earth. Even if Earth somehow avoids being swallowed, its surface will be scorched. Life cannot survive. During the red giant phase, the star's outer layers become extremely thin, while the core continues to contract and heat under gravitational pressure. When the core temperature finally reaches approximately 100 million Kelvin, a dramatic event occurs. The helium flash, under the peculiar physical conditions of degenerate matter. Helium fusion ignites in a near-explosive manner, releasing energy equivalent to the entire Milky Way galaxy within mere minutes. However, most of this energy is absorbed by the star itself. To relieve the degenerate state of its core, observed from the outside, we would only witness the star undergoing a brief adjustment before entering a relatively stable phase of helium core burning. On the Hertzsprung-Russell diagram, the star would shift leftward and settle on the horizontal branch. For the Sun, the red giant phase will last approximately 2 billion years, when the helium in the core is also exhausted, and it becomes a degenerate core composed of carbon and oxygen. The star will once again experience instability. Alternating shell burning of hydrogen and helium causes the star to periodically pulsate and eject material. At this stage, the star becomes a pulsating variable star, such as a Cepheid variable or an RR-Lyrae variable. These stars are crucial to astronomy because their pulsation periods are fixedly related to their true luminosity, making them reliable rulers for measuring cosmic distances. After several violent ejections of material, the star's outer layers are expelled into interstellar space, forming a colorful, luminous cloud, known as a planetary nebula. This name stems from a historical misunderstanding. Early astronomers observing through small telescopes noticed their disk-like appearance resembling planets, hence the name planetary nebula. In reality, they bear no relation to planets. They are products of the final stages of stellar evolution. The Cat's Eye Nebula, Ring Nebula, and Ring Nebula are all renowned examples. This ejected material is rich in heavy elements synthesized within the star's core and will return to the interstellar medium to become the raw material for the birth of a new generation of stars and planets. At the center of the planetary nebula lies the star's scorching, dense core, a white dwarf. White dwarfs are formed when electron degeneracy pressure counterbalances gravity. Though comparable in mass to the Sun, their volume is roughly that of Earth. A single teaspoon of white dwarf material weighs tens of tons. Nuclear fusion ceases, and it cools slowly through residual heat. Over billions of years, it fades from blazing white to dim red, eventually transforming into a cold, dark dwarf. serving as a cosmic tombstone for the star. Yet no white dwarf in the universe has cooled to the dark dwarf stage, because the time required for this process exceeds the current age of the universe. Compared to the peaceful end of low-mass stars like the Sun, the twilight of massive stars unfolds as a cosmic fireworks display. Stars exceeding 8 solar masses live lives like tightly paced dramas. They burn fuel at astonishing rates, spending only millions to tens of millions of years on the main sequence. When their core hydrogen is exhausted, they skip the helium flash and transition smoothly into helium burning, expanding into red supergiants. Take Betelgeuse in Orion, for example. If its diameter were placed at the center of our solar system, it would extend beyond Jupiter's orbit. The core of a massive star resembles an onion, exhibiting a layered combustion structure. At its very center lies an iron core, followed outward by layers burning silicon, sulfur, oxygen, helium, and carbon. The outermost layer contains unburned hydrogen. Each layer undergoes nuclear fusion reactions of different elements. This provides the star with its energy. Yet this intricate structure is destined to collapse. Iron possesses the highest average binding energy among all elements. Fusion within iron does not release energy. Instead, it consumes energy. Thus, the iron core becomes an endpoint that absorbs energy without producing it. When the mass of the iron core exceeds the Chandrasekhar limit, electron degeneracy pressure can no longer counteract its own gravity. The iron core will undergo gravitational collapse at an astonishing rate. Within 1/10 of a second, the energy released during this process is so immense that it triggers a violent supernova explosion, hurling the star's outer layers into space at speeds exceeding thousands of kilometers per second. Supernova explosions are the universe's most spectacular fireworks, their instantaneous brightness surpassing that of entire galaxies. Within mere weeks, they release energy equivalent to the entire lifetime output of the Sun. During this process, extreme temperatures and pressures create the conditions. All elements heavier than iron, including familiar metals like gold, silver, platinum, and uranium, the gold jewelry you wear, and the rare earth elements in your electronics, all trace back to ancient supernova explosions. We are literally children of stardust. The remnants left after a supernova explosion depend on the core's remaining mass. If the core mass lies between approximately 1.4 to 3 times the mass of the Sun, gravity overcomes electron degeneracy pressure, forcing electrons into atomic nuclei to combine with protons and form neutrons. This ultimately creates a celestial body supported by neutron degeneracy pressure. A neutron star, a typical neutron star, has a diameter of only about 20 kilometers, yet compresses over 1.4 times the mass of the Sun. Its density is unimaginably high. A single teaspoon of neutron star material could weigh billions of tons. Neutron stars typically spin rapidly, some rotating hundreds of times per second, emitting regular radio pulses along their magnetic axis. Such neutron stars are called pulsars, acting as cosmic lighthouses. If the collapsed core exceeds 3 solar masses, even neutron degeneracy pressure cannot withstand gravity. Matter is compressed into an infinitely dense singularity, forming a black hole, a region where gravity is so powerful that not even light can escape. Black holes themselves are invisible, but their presence can be inferred through their powerful effects on their surroundings, such as the intense X-ray radiation emitted by their accretion disks. The life cycle of a star is a billion-year-long tug-of-war between mass and gravity, from the steady burning of main-sequence stars, to the magnificent expansion of red giants, to the tranquil embers of white dwarfs. or the violent explosions of supernovae, and the bizarre endings of neutron stars and black holes. Each star writes its own cosmic tale, in its unique way, and enriches the interstellar medium with the gifts of its final moments, sowing seeds of hope for the emergence of the next generation of stars, planets, and life. When we gaze upon the night sky, we see not merely eternal points of light, but cosmic torches at different stages of their existence. Their birth and demise weave the cosmic epic of material cycles and evolution, and we ourselves are but the latest chapter in this grand saga. When we gaze upon the myriad stars in the night sky, or feel the rhythms of life on Earth, we are witnessing a cosmic alchemy spanning billions of years. At the heart of this alchemy lies a process called nucleosynthesis. It forged all the chemical elements in the universe, and provided the fundamental building blocks for life as we know it. Let us return to the beginning of time, to the very first moment of the universe's birth. In the initial minutes after the Big Bang, the universe was an intensely hot and dense primordial fireball. During this brief period known as Big Bang nucleosynthesis, the universe's temperature and density were sufficient for fundamental particles to begin combining. Protons and neutrons formed the earliest atomic nuclei through nuclear reactions. This process created the most primordial elements in the cosmos. By the end of the Big Bang nucleosynthesis, approximately 3/4 of the universe's matter was hydrogen, 1/4 was helium, with trace amounts of lithium and deuterium. This was the primordial elemental recipe of the cosmos. Simple yet foundational to all existence. Every subsequent, more complex element would be built upon these light elements. The Big Bang nucleosynthesis process lasted about 20 minutes. As the universe rapidly expanded and cooled, nuclear reactions soon ceased, because the particles' energy was no longer sufficient to overcome their mutual electromagnetic repulsion. Over the subsequent hundreds of millions of years, the universe resembled a primordial soup composed of hydrogen and helium, sprinkled with trace amounts of lithium, awaiting the emergence of the first stars to initiate the next phase of creation. When the first generation of stars ignited across the cosmos, they ushered in a new era of element creation, stellar nucleosynthesis. Deep within the blazing cores of stars, extreme heat and pressure provide ideal conditions for nuclear fusion reactions. Hydrogen nuclei collide and fuse into helium. This process not only releases the energy sustaining a star's light and heat, but also initiates the chain of element creation. For sun-like stars of moderate mass, nuclear fusion proceeds relatively gently, primarily through the proton-proton chain reaction, gradually transforming hydrogen into helium. When core hydrogen is exhausted, stars initiate helium fusion, producing carbon and oxygen. Yet, for most stars of this mass, their capabilities end here, unable to forge heavier elements. For more massive stars, however, the story unfolds entirely differently. Massive stars function like multi-layered nuclear reactors. At different stages of a star's life, various elements are sequentially synthesized in distinct layers of the core. The innermost region, where temperatures are highest, hosts the fusion of the heaviest elements. Outward layers progressively burn lighter elements. This onion-like structure enables massive stars to create elements spanning the periodic table from hydrogen to iron. But this path of creation hits a roadblock at iron. The iron nucleus possesses the highest average binding energy of all elements. This means that when lighter elements fuse into iron, energy is released. Conversely, fusing iron into heavier elements requires energy input. Within the stellar core, iron acts as an energy terminal, It no longer supplies the energy needed to sustain the star's radiation pressure. This turning point signals the imminent, dramatic conclusion of the star's life. When a massive star's core solidifies into iron and grows to a certain size, its fate is sealed. Deprived of energy support, the iron core collapses catastrophically under its own gravity. In less than a second, the immense energy released during this collapse ignites a supernova explosion, violently ejecting the star's outer layers into interstellar space. Under the extreme conditions of a supernova explosion, two crucial processes for heavy element synthesis come into play. The first is the slow neutron capture process, commonly referred to as the S process. This process primarily occurs during the red giant phase, where neutrons are slowly captured by atomic nuclei. Through a series of beta decays, heavier elements between iron and bismuth are progressively built. The second is the rapid neutron capture process, commonly referred to as the R process. This is a unique product of supernova explosions. Within an extremely short time frame, the rate at which atomic nuclei capture neutrons far exceeds their decay rate, thereby creating all heavy elements from iron to uranium and beyond, including precious metals like gold, silver, and platinum, as well as radioactive elements such as uranium and thorium. However, in recent years, astronomers have discovered another potentially more significant source of heavy elements: neutron-star mergers. When neutron stars, the densest objects in the universe, orbit each other and eventually collide, they generate physical conditions even more extreme than those in supernovae. The gravitational wave event GW 170817, observed in 2017, accompanied by the optical counterpart of a 1000 star, provided conclusive evidence, proving neutron-star mergers are indeed one of the primary cosmic factories for heavy elements. In these extreme astrophysical events, ejected neutron-star material produces vast quantities of heavy elements through the R process. Estimates suggest a single neutron-star merger can generate hundreds of Earth masses worth of gold and platinum. These newly synthesized elements are scattered into interstellar space, where they mix with gas clouds, becoming raw material for the next generation of stars and planetary systems. As we trace the cosmic journey of these elements, a profound truth emerges. Every atom that makes up our world and ourselves carries an extraordinary cosmic history. The iron atoms transporting oxygen in your blood likely originated in the core of an ancient massive star, where they underwent millions of years of nuclear fusion before finally being liberated in the fiery explosion of a supernova. The calcium in your bones, the oxygen you breathe, the sodium and potassium essential for your nerve signals, all these elements vital to life, were forged within a star, or created in the explosion of a supernova. And those more precious elements share equally extraordinary origins. The gold ring you wear may have originated from the violent collision of two neutron stars. In some corner of the cosmos, these two dense celestial bodies orbited each other for millions of years, finally merging into a black hole, while ejecting a portion of neutron-rich matter into the universe. As this matter expanded and cooled, gold was synthesized through the R process. After millions of years of interstellar travel, it eventually reached Earth, becoming the ornament in your hand, the rare Earth elements in your electronics, the radioactive elements used in medical diagnostics, even the uranium fuel powering nuclear reactors, all share a similar cosmic origin, forged in extreme stellar events. This realization forges a profound connection between us and the universe. We often perceive the cosmos as distant and external, yet the science of nucleosynthesis reveals The universe resides within us. Every atom in our bodies has witnessed the most violent, spectacular events in the cosmos. We are not merely living in the universe. We are part of the universe, a way for the universe to recognize itself. This connection is not merely poetic imagination, but rests on solid scientific foundations. Through spectral analysis, we can determine the elemental composition of stars and nebulae. Through nuclear physics experiments, we can recreate the nucleosynthesis processes of the cosmos. Through computer simulations, we can trace the cyclical history of elements within galaxies. All evidence points to the same conclusion. The matter that forms Earth and life originated from nucleosynthesis in the cosmos. When we realize this, our view of the cosmos undergoes a fundamental shift. The stars in the night sky are no longer distant points of light unrelated to us, but our creators and ancestors. Interstellar space is no longer a void of emptiness, but a womb brimming with future possibilities. And we ourselves are the latest manifestation in the cosmic river of material evolution. This realization compels us to reconsider the preciousness of life. In the cosmos, hydrogen and helium dominate the material composition. The heavier elements essential for life, in fact, constitute only a minuscule fraction of the universe's total matter. These heavy elements require the life and death cycles of multiple generations of stars to accumulate sufficient abundance. Only when these elements combine in precisely the right ways does life emerge. Our existence depends on the diligent work of countless stars over the past 10 billion years. Each stellar generation contributes to the universe's elemental abundance. Supernova explosions scatter newly synthesized elements into interstellar space. Planetary nebulae gently release carbon and oxygen-rich outer layers of stars. Merging neutron stars deliver the heaviest elements. All this material mixes within the interstellar medium. Ultimately, some of it coalesces to form our solar system. Thus, when we say we are all stardust, it is not merely a poetic expression, but an accurate description of the cosmic cycle of matter. The carbon, nitrogen, and oxygen in our bodies primarily originate from the final stages of life in medium to low mass stars. Elements like sodium, magnesium, and silicon within us, mostly formed in the cores of massive stars. The heavier elements we possess, gold, silver, platinum, likely originated from neutron star mergers or supernova explosions. With every breath, we inhale oxygen atoms forged within stars. With every heartbeat, we use iron atoms born in supernova explosions to transport oxygen. With every thought, we rely on elements synthesized in stellar cores to sustain neural activity. We are the product of cosmic chemical evolution, a temporary assemblage of stellar matter, bearing the history of the universe's past 10 billion years. This realization makes us feel both insignificant, for we are but transient travelers in the cosmos, and yet profoundly significant, for we are the universe's means of self-recognition. In the vast cosmos, among countless galaxies and stars, on the third planet of an unremarkable star system, matter in the universe has temporarily organized itself into a form capable of contemplating its own origins. This in itself is a miracle worthy of wonder. As we conclude this exploration of the origins of elements, let us return to daily life with renewed awareness. Each time we see a metal object, each time we feel our own breath, each time we observe the natural world around us, we can recall the cosmic story behind these elements. They have journeyed through the vastness of space, spanning immense scales of time and space, to ultimately become part of our world and ourselves. In this sense, Our connection to the universe is so profound that we can proudly declare, we are the universe's way of contemplating itself. It is stellar matter that gained life and consciousness. It is cosmic chemistry that reached the stage of self-awareness. This realization grants us a profoundly new understanding and deep reverence for the universe, for life, and for ourselves. Within this cosmic temple built of elements, each of us is both ordinary and extraordinary, both an observer and the observed cosmos itself. In the realm of astronomy, stars are not merely points of light in the night sky. They are chroniclers of cosmic history. The atmospheric composition of every star preserves information about the cosmic environment during its formation. Just as tree rings record climatic shifts, a star's chemical composition chronicles the material evolution of the universe. To understand the relationship between stars and cosmic evolution, astronomers developed the concept of stellar populations. This framework classifies stars based on their chemical composition, spatial distribution, and motion characteristics, helping us unravel the complex history of the Milky Way. Stellar populations are primarily divided into three categories. Each represents a distinct phase in cosmic evolution. Population 1 stars constitute the youngest stellar group. They are metal-rich. Here, metals in astronomy refer to any element heavier than helium. Population 1 stars are predominantly distributed across the Milky Way's galactic disk, particularly within the spiral arms. They orbit the galactic center along nearly circular paths. Our Sun is a classic example of a population 1 star, with a metallicity of approximately 1.4%. These relatively young stars formed during the later stages of the Milky Way's evolution, when heavier elements had already accumulated to significant abundances through the life cycles of previous stellar generations. In stark contrast to population 1 stars are population 2 stars. These ancient stars exhibit markedly low metallicity. They are primarily distributed in the Milky Way's halo and globular clusters. Population 2 stars typically exhibit orbits with high eccentricity and inclination. Unlike population 1 stars, which orbit the galactic center in a regular manner, they move in highly inclined elliptical orbits above and below the galactic disk. This orbital characteristic suggests they formed during the early stages of the Milky Way's evolution, before the galaxy had developed its flat, disk-like structure. The most enigmatic are population 3 stars. These are the theoretical first generation of stars, composed of primordial material from the Big Bang nucleosynthesis. They contain almost no heavy elements. To date, astronomers have not directly observed population 3 stars. Because their lifetimes were extremely short, they perished in the early universe. However, through their influence on subsequent star formation, we can indirectly detect their presence. Within the Milky Way, we can distinguish halo stars from disk stars based on their dynamical characteristics. Halo stars primarily refer to population 2 stars. They are distributed in the galactic halo. Their orbits are highly elliptical and exhibit significant inclination relative to the galactic plane. These stars resemble archaeological sites within the Milky Way, preserving the oldest information in the universe. Disk stars, on the other hand, are predominantly population 1 stars. They are concentrated within the galactic disk. Their orbits are nearly circular and remain almost entirely within the galactic plane. These stars represent a relatively young population within the Milky Way. They formed after the establishment of the galactic disk structure and carry the Milky Way's more recent history. Chemically, halo and disk stars exhibit distinct differences. Halo stars typically possess very low metallicity, with iron-to-hydrogen ratios potentially as low as 1% or even 1,000th of the Sun's. This indicates their formation in the early universe, before earlier stellar generations had time to contaminate the interstellar medium. Disk stars, conversely, exhibit high metallicity, reflecting that during their formation, the interstellar medium had already been enriched by nucleosynthesis products from preceding generations of stars. This chemical disparity extends beyond heavy elements like iron to specific elemental ratios, such as the alpha element to iron ratio. Alpha elements include oxygen, neon, magnesium, silicon, sulfur, calcium, and titanium, primarily synthesized in the cores of massive stars and ejected into interstellar space during supernova explosions. By studying these elemental ratios, astronomers can trace different aspects of stellar formation history. Halo stars typically exhibit high alpha iron ratios, indicating they formed in the early universe when star formation rates were high, and massive stars dominated nucleosynthesis. Disk stars, conversely, show low alpha iron ratios, reflecting that during their formation, galactic star formation had entered a more stable phase. Among these ancient stars, one stands out particularly: HD 140,283, located in the constellation Libra, approximately 190 light-years from Earth. This star is known as the Methuselah star, famous for its extreme age. Astronomers have determined its age through multiple methods, including its extremely low metallicity, precise parallax measurements, and detailed stellar evolution models. The latest research indicates HD 140,283 is approximately 13.6 billion years old, with a margin of error of plus or minus 800 million years. This age is astonishing, as it approaches the currently measured age of the universe, of 13.8 billion years. This implies the star must have formed in the very early universe, possibly within just a few hundred million years after the Big Bang. HD 140283 exhibits an extremely low metallicity, with an iron-to-hydrogen ratio only 1/250th that of the Sun, indicating the interstellar medium in which it formed had not yet been sufficiently contaminated by previous generations of stars. Its chemical composition preserves the characteristics of the universe's earliest era, like a well-preserved ancient manuscript, recording information from the cosmos' infancy. Studying such ancient stars holds immense scientific value. They are living fossils of the early cosmos. By analyzing their spectra, astronomers can uncover the properties of the first generation of stars, test predictions of Big Bang nucleosynthesis, and refine our understanding of the earliest stages of galaxy formation. The existence and properties of these ancient stars impose stringent constraints on cosmological models. Their age must be less than the age of the universe. Their chemical composition must match predictions of Big Bang nucleosynthesis. Their spatial distribution and motion characteristics must align with theories of galaxy formation. Through systematic studies of metal-poor stars, astronomers are mapping the growth history of the Milky Way. Each ancient star is like an artifact in galactic archaeology. Their positions, trajectories, and chemical compositions collectively narrate the evolutionary story of how the Milky Way grew, from small to large, from simple to complex through mergers and accretion. Within the Milky Way's halo, astronomers have identified multiple stellar streams with distinct chemical and dynamical signatures. These are remnants of dwarf galaxies torn apart and consumed by the Milky Way. Stars within these streams often share similar chemical compositions and motion directions, much like family members bearing identical DNA. By tracing these stellar streams, astronomers can reconstruct the Milky Way's merger history, determining when and how these satellite galaxies were devoured. This method of galactic archaeology offers a unique perspective on galaxy formation. Most intriguingly, among these ancient stars, we may find direct descendants of the universe's first generation of stars. Though population 3 stars themselves have perished, they injected the first heavy elements into the interstellar medium through supernova explosions. These elements were absorbed by subsequent stellar generations, forming the extremely metal-poor stars we observe today. By studying the chemical composition of these extremely metal-poor stars, astronomers can indirectly infer the properties of the first generation of stars, such as their mass distribution, nucleosynthesis processes, and how they ended their lives. This information is crucial for understanding the earliest star formation in the universe and the reionization process. When we gaze at the night sky, those seemingly ordinary stars each carry distinct cosmic histories. Young population 1 stars, like our Sun, tell us the recent story of the Milky Way. Meanwhile, ancient population 2 stars, such as HD 140283, transport us back to the dawn of the universe. These ancient survivors are not merely objects of astronomical observation. They are bridges connecting us to the origins of the cosmos. By studying them, we can trace the origins of the elements that compose our bodies, understand how our universe evolved from simplicity to complexity, from homogeneity to structure. In this sense, each metal-poor star is a time capsule, preserving memories of the cosmos' infancy. They quietly shine in the night sky, awaiting our interpretation of the cosmic secrets they hold. These secrets concern not only the past, but also how we comprehend the universe's present and future. Through the study of stellar populations and metal-poor stars, we are gradually unveiling the magnificent panorama of cosmic chemical evolution. This panorama connects the past, present, and future of the universe, bridging the largest cosmic scales with the smallest atomic nuclei, and linking us humans to the vast cosmos. At the endpoint of stellar evolution, when the flames of nuclear fusion extinguish, gravity becomes the absolute ruler. The universe forges 2 most extreme forms of matter, neutron stars and black holes. These dense celestial bodies represent not only gravity's ultimate triumph, but also laboratories for physical laws under extreme conditions. Their existence challenges our imagination and deepens our understanding of the cosmos. Neutron stars are the remnants of massive stellar supernova explosions. When a star's core mass lies between 1.4 and 3 times that of the Sun, electron degeneracy pressure can no longer resist gravity. Matter is compressed to the density of atomic nuclei. Electrons are forced into the nucleus, combining with protons to form neutrons. Ultimately, a celestial body supported by neutron degeneracy pressure emerges. This is the neutron star, a typical neutron star, with a mass roughly 1.4 times that of the Sun, is compressed into a sphere just 20 kilometers in diameter. Its density reaches hundreds of millions of tons per cubic centimeter, equivalent to compressing the entire Himalayas into the size of a sugar cube. At such extreme densities, the state of matter becomes alien and bizarre. The neutron star's outer shell consists of a rigid crystalline layer of iron nuclei. Its interior is a superfluid neutron sea. At its core may lie exotic quark matter. When a neutron star forms, it inherits the angular momentum of its progenitor star's core, due to its drastically reduced diameter and the conservation of angular momentum. Its rotational speed increases dramatically. A newborn neutron star can spin hundreds of times per second. Simultaneously, it compresses the progenitor star's magnetic field. intensifying it to trillions of times that of an ordinary star. This rapid rotation, coupled with an ultra-strong magnetic field, creates the most precise clock in the universe, the pulsar. As a pulsar spins, its magnetic axis typically misaligns with its rotational axis. Beams of radiation emitted from its magnetic poles sweep across the cosmos like a lighthouse's beam. Whenever this radiation beam points toward Earth, we receive a pulse signal. The discovery of pulsars marked a monumental breakthrough in 20th century astronomy. In 1967, Jocelyn Bell discovered remarkably regular periodic signals while analyzing radio telescope data. Initially, these were even mistaken for signals from extraterrestrial civilizations. We now understand these cosmic lighthouses possess unparalleled stability. Some pulsars exhibit rotational stability surpassing that of atomic clocks. This astonishing stability gives pulsars unique practical value. Astronomers use pulsar timing arrays to detect gravitational waves. By monitoring minute variations in the arrival times of pulses from multiple millisecond pulsars, low-frequency gravitational waves from supermassive black hole mergers can be detected. This opens a new window for observing the universe. Pulsars can also serve as navigational beacons for space travel. Their signals propagate through space with remarkable stability and predictability, potentially offering a natural GPS system for deep space navigation in the future. Certain special pulsar binary systems also provide extreme laboratories for testing general relativity. Yet, even these extraordinary neutron stars represent not the ultimate limit of gravitational compression. When stellar remnants exceed 3 solar masses, even neutron degeneracy pressure fails to resist gravitational collapse. Matter continues to collapse, forming the most mysterious objects in the universe, black holes. At the center of the Milky Way, astronomers have found conclusive evidence of a supermassive black hole, Sagittarius A*. The location of this mysterious radio source corresponds precisely to the galactic center of mass. Over the past 2 decades, astronomers have continuously tracked the motion of multiple stars near the galactic center, particularly the star designated S2. Its trajectory exhibits an extremely elliptical orbit, coming as close as 17 light-hours to the galactic center. During this orbit, the speed reaches up to 3% of the speed of light. By precisely measuring the orbital parameters of these stars, astronomers can calculate the mass of the central object. The results indicate, within an area smaller than Mercury's orbit, approximately 4.3 million solar masses are concentrated. Such immense mass concentrated in such a small space can only be explained by a supermassive black hole. Beyond stellar orbital evidence, we also observe the radiation characteristics of Sagittarius A*. Though relatively quiet most of the time, periodically exhibits flare events, where radiation is emitted as matter is heated to millions of degrees. In the accretion disk before being swallowed by the black hole, observations from the Event Horizon Telescope have provided us with a direct image of the black hole's shadow. This network of radio telescopes worldwide achieved unprecedented angular resolution, sufficient to resolve the structure of Sagittarius A*'s event horizon. Though Sagittarius A** possesses immense mass, the diameter of its event horizon is only about 24 million kilometers. Compared to the Milky Way's scale of hundreds of thousands of light-years, it is minuscule. Yet this tiny gravitational abyss governs the entire galaxy, influencing the motion of hundreds of billions of stars. Compared to supermassive black holes, stellar mass black holes are more common. Formed by the direct collapse of massive stars, their masses typically range from 3 to 100 times that of the Sun. Detecting these black holes presents a challenge. as they emit no light themselves. We can only detect them indirectly through their interactions with their surroundings. The most common method involves X-ray binary systems. When a black hole forms a binary system with an ordinary star, it can accrete material from its companion star. As this material falls toward the black hole, it forms a rotating accretion disk. Heated to extremely high temperatures by friction, the disk emits intense X-ray radiation. Cygnus X1 was the first widely recognized black hole candidate. This powerful X-ray source harbors a black hole approximately 21 times the mass of the Sun. It forms a binary system with a blue supergiant star. By analyzing the orbital motion of this binary pair, we can precisely determine the black hole's mass. The recent emergence of gravitational wave astronomy has revolutionized black hole research. When two black holes orbit each other and eventually merge, they generate ripples in spacetime, gravitational waves. The Laser Interferometer Gravitational Wave Observatory and Virgo interferometers have detected dozens of black hole merger events. These observations reveal an unexpected phenomenon: a vast population of black holes with masses tens of times greater than the Sun. These black holes exceed the mass limits predicted by traditional supernova theories, suggesting stellar evolution may be more complex than previously imagined. Even more surprising, some black holes possess masses exceeding 100 solar masses. These likely aren't formed by the collapse of a single star, but result from gradual growth through multiple mergers. By analyzing these gravitational wave events, we can also study black hole spin, the merger process, and test general relativity's predictions in strong gravitational fields. Each detected black hole merger provides new clues for understanding these mysterious celestial bodies. Within the Milky Way, millions to hundreds of millions of stellar mass black holes are estimated to exist. Most drift solitarily through interstellar space, making them difficult to detect. Only those actively accreting matter, or participating in gravitational wave events, reveal their presence. Astronomers have recently discovered intermediate mass black holes, whose masses lie between stellar mass and supermassive black holes. These black holes may serve as seeds for supermassive black hole growth, or result from multiple mergers within globular clusters. Their discovery fills gaps in the black hole mass spectrum, from pulsars' precise clocks to black holes' gravitational abysses. These compact objects reveal the limits of physical laws. They mark not only the end of stellar life, but also the beginning of new discoveries. Each observation of these extreme objects expands the frontiers of human knowledge. The steady pulse of a pulsar allows us to detect the faintest ripples in spacetime. The shadow image of a black hole enables direct observation of the event horizon structure. Such achievements would have been unimaginable decades ago, yet they are now routine tools in astronomical research. When we gaze toward the center of the Milky Way, we know a gravitational colossus reigns over hundreds of billions of stars. When we listen to the rhythmic signals from pulsars, and sense such precise timekeepers exist in the cosmos, we cannot help but marvel at the wonders of the universe, and take pride in humanity's ability to comprehend these miracles. The study of these compact objects is far from over. Next-generation gravitational wave detectors, more sensitive X-ray telescopes, and higher-resolution radio interferometry arrays will all bring us new discoveries. Perhaps we will find the missing link connecting neutron stars and black holes. Perhaps we will discover new types of compact objects. Perhaps we will gain entirely new insights into how matter behaves under extreme densities. In this journey of exploration, every new observation and every theoretical breakthrough continues to reshape our understanding of the universe. As the most extreme laboratories in the cosmos, compact objects will keep challenging our imagination. Now relax your breathing and let your thoughts drift toward those solitary travelers in the Milky Way. Unbound by any star, they traverse the vast interstellar space alone. These cosmic wanderers each face distinct fates, yet all narrate the dynamic evolution of our galaxy. First, let us meet the most elusive wanderers, rogue planets. They orbit no star, drifting alone through the interstellar darkness. These planet-sized bodies typically possess masses comparable to Earth or Jupiter, yet deprived of a host star's illumination. They remain nearly invisible in the visible light spectrum. Rogue planets form through two primary pathways. Some, like ordinary planets, form within the protoplanetary disks of young stars, but are later ejected from their planetary systems through gravitational interactions, like a ball knocked off a billiard table, forever departing their birthplace. Alternatively, they may form directly within interstellar space, when small molecular cloud cores lack sufficient mass to trigger hydrogen fusion. They may collapse directly into planet-mass objects. These bodies never experienced a star's warmth, doomed from birth to drift in perpetual cold. Deprived of stellar light and heat, rogue planets possess extremely low surface temperatures, typically only a few dozen degrees above absolute zero. They may harbor atmospheres composed of hydrogen and helium, or be shrouded in thick layers of water ice. Driven by the faint heat generated by internal radioactive decay, some rogue planets may exhibit geological activity lasting billions of years. Detecting these solitary travelers in the darkness poses significant challenges. Astronomers primarily seek them through the microgravitational lensing effect. When a rogue planet passes directly in front of a background star, this gravity bends and magnifies starlight like a lens, causing the background star to briefly brighten. By analyzing the characteristics of this brightness change, we can infer the mass and other properties of the intervening object. Recent observational data suggests the number of rogue planets in the Milky Way may far exceed our imagination. Some estimates suggest their total could surpass 100 billion, even outnumbering the stars in the galaxy. This implies that within the dark spaces between the stars lies a hidden planetary world. Unlike these slow-drifting dark planets, hypervelocity stars are the galaxy's most radical escapees, moving at hundreds of kilometers per second, fast enough to escape the galaxy's gravitational grasp, and ultimately vanish forever into intergalactic space. Why do these stars move so rapidly? The answer lies in the galaxy's most dangerous region, near the supermassive black hole at its center. When a binary star system ventures too close to this gravitational behemoth, the black hole's immense tidal forces tear the pair apart. One star is captured by the black hole, while the other is ejected at extreme velocities. This process resembles a cosmic slingshot effect, but powered by gravity instead of rubber bands. Another possibility arises when a supernova explodes near the black hole. An asymmetric blast could catapult the companion star like a projectile. Regardless of the exact mechanism, these stars endure one of the universe's most violent events. To achieve such astonishing speeds, hypervelocity stars are predominantly massive blue stars, with short lifespans yet extraordinary brightness. They streak across the Milky Way's halo like meteors, leaving behind a fading trail of starlight. Astronomers identify these fugitives by measuring their radial velocities and proper motions. Some hypervelocity stars even exceed the Milky Way's escape velocity, doomed to embark on a journey of no return. The fate of these stars is poignant. They will traverse intergalactic space alone, where matter density is a millionth that of the Milky Way. When their nuclear fuel is exhausted, they may end their lives in utter solitude, with no companions to witness their final moments. Yet, among these wanderers' tales, the most spectacular may be stellar streams. These vast structures, composed of thousands of stars, like shimmering ribbons coiled around the Milky Way. They stand as direct evidence of galaxy mergers and interactions, recording the Milky Way's history of devouring others. The most famous, the Sagittarius Stream, is the remnant of a dwarf galaxy being torn apart by the Milky Way. This former galaxy has now been stretched into a chain of stars spanning tens of thousands of light-years. Its stars move along similar orbits, like a cosmic river flowing through the Milky Way's halo. The formation of stellar streams is a slow and elegant process. When a small galaxy comes too close to the Milky Way, tidal forces begin to take effect. The side closer to the Milky Way experiences stronger gravitational pull, while the opposite side experiences weaker pull. This difference gradually stretches the small galaxy, first forming tidal tails. Over time, these tails grow longer and longer, eventually encircling the entire Milky Way. By studying these stellar streams, astronomers can conduct galactic archaeology, much as geologists read Earth's history through rock layers. Through the shape and motion of stellar streams, we can reconstruct the timing and process of merger events. Each stellar stream is like an open history book, recording an ancient cosmic encounter. The spatial distribution of stars within the stream reveals when the merger occurred. Their chemical composition unveils the primordial nature of the devoured galaxy, while their trajectories preserve the dynamics of the interaction. Beyond the Sagittarius Stream, the Milky Way hosts numerous other stellar stream structures. Some originate from the disintegration of globular clusters. Others are remnants of larger galaxy mergers. Precise measurements from the Gaia Space Telescope have uncovered an increasing number of such structures, interwoven around the Milky Way, forming a complex archaeological record. These stellar streams are not eternal. Over time, they gradually dissipate, blending into the Milky Way's background stellar field. This process typically spans timescales of billions of years. Thus, observed stellar streams correspond to relatively recent merger events. Studying these structures concerns not only the past, but also the future. By understanding the process of galaxy mergers, we can predict the detailed scenario of the future collision between the Milky Way and Andromeda. Stellar streams act like simulations in a laboratory, allowing us to glimpse the ultimate fate of galactic evolution. When we turn our gaze to these cosmic wanderers, from icy rogue planets to fiery hypervelocity stars, to the sprawling stellar streams, we witness a dynamic, ever-changing Milky Way, where gravity acts as both creator and destroyer, shaping order while unleashing chaos. These celestial bodies remind us that our galaxy is not a static island, but a living, breathing, growing cosmic organism. Every wandering star, every stream of starlight, bears witness to this organism's growth journey, perhaps beneath the ice of some rogue planet, or in the warmth of deep-sea hydrothermal vents. Life is quietly emerging, though it may never see the sun in the sky. The energy provided by geothermal heat might sustain a unique ecosystem. Such life forms would forever remain unaware of the cycle of day and night, surviving in eternal darkness, sustained only by the planet's internal heat. As for those hypervelocity stars, though they will forever depart the Milky Way, perhaps millions of years hence, they will carry the galaxy's tail into another star system's embrace, becoming cosmic messengers, transmitting messages from our home. Within this grand cosmic perspective, Wandering ceases to be solitude or exile, but becomes a new mode of existence. These celestial bodies trace their own paths, compose cosmic poems distinct from ordinary stars. They teach us that even in the most extreme environments, order and beauty persist. Now, as your thoughts wander through the cosmos, feel the journeys of these wanderers. Their destinies may be distant, yet their stories resonate deeply with ours. For we all dwell within the same galaxy, part of this cosmic drama of evolution. Let the tales of these distant travelers lull you to sleep. Know that in the vast cosmos, even the loneliest journey holds profound meaning, and our Milky Way, this home woven from 100 billion stars, still dances in the embrace of gravity, continuing its evolution and growth. Now take a deep breath. Feel the invisible sea of energy surrounding us. The Milky Way is not only composed of stars and planets, but also filled with invisible forces and particles. Together, they form a vibrant, high-energy universe. Large-scale magnetic fields exist within the Milky Way. Though their strength is only 1/10,000th that of Earth's magnetic field, on scales spanning tens of thousands of light-years, they shape the structure and motion of the interstellar medium. This magnetic field is not uniform or static, but resembles a complex tapestry, with varying orientations and intensities. Astronomers detect the galactic magnetic field through multiple methods. When starlight traverses dust-filled interstellar space, dust particles cause it to become polarized. By measuring this polarization, we can infer the orientation of the magnetic field. Additionally, synchrotron radiation within the interstellar medium provides valuable information about the magnetic field. This radiation is emitted by relativistic electrons moving within magnetic fields, and its polarization characteristics directly reflect the direction of the magnetic field. The galactic magnetic field exhibits a multi-layered structure. In the spiral arm regions, the magnetic field is largely aligned along the spiral arms and is relatively strong. In the interarm regions, the magnetic field is more disordered and relatively weaker. This distribution indicates that the magnetic field's morphology is closely tied to the Milky Way's spiral structure and may have co-evolved during the galaxy's formation. Magnetic fields play a crucial role in the dynamics of the interstellar medium by influencing the collapse of gas clouds and the formation of stars. When sufficiently strong, magnetic fields can counteract gravity to delay or prevent star formation. They also constrain high-temperature plasma and guide the propagation of cosmic rays, much like an invisible magnetic belt encircling the galaxy. Beyond this invisible magnetic skeleton, the Milky Way teems with various high-energy particles, cosmic rays being one such example. These are atomic nuclei bombarding Earth from space, primarily protons, but also including helium nuclei and heavier elements. Traveling at speeds approaching light, they carry astonishing energy. The origin of cosmic rays has long been a major topic in astrophysics. We now know supernova remnants serve as their primary accelerators. When shock waves generated by supernova explosions propagate through interstellar medium, they function like gigantic particle accelerators. Through Fermi acceleration mechanisms, they boost charged particles to extremely high energies. These particles then travel through the Milky Way's magnetic field, with some eventually reaching Earth. As you read these words, thousands of cosmic rays pass through your body every second. Most originate from distant supernova explosions. These invisible messengers carry information about high-energy processes in the Milky Way. While generally harmless to life, during space travel, cosmic rays present a radiation hazard that must be taken seriously. Above and below the galactic center stretch two immense structures, the Fermi bubbles. They resemble two giant balloons blown from the galactic center. Each bubble extends tens of thousands of light-years in height and glows brightly in the gamma-ray spectrum. The discovery of these bubbles is credited to the Fermi Gamma-Ray Space Telescope. They were first identified in 2010. Though invisible to the naked eye, specialized detectors allow us to map their majestic forms. The bubbles' edges are remarkably sharp, suggesting they may have formed during a relatively rapid energy release event. Regarding the origin of the Fermi bubbles, scientists have proposed multiple theories. One perspective suggests they may be remnants of outflows from the supermassive black hole at the Milky Way's center. During a past period of intense activity, when the black hole devours vast amounts of matter, it generates powerful jets, transporting energy and material outward from the galactic core. Another theory posits these bubbles could originate from starburst activity in the central region, when massive stars form rapidly in a short period, and then die in supernova explosions. The immense energy released could inflate such bubbles. Regardless of the specific mechanism, these structures reveal that the galactic center was far more active in the past. Beyond these distinct structures, the Milky Way is also permeated by diffuse background radiation. Across the gamma-ray and X-ray bands, the entire sky emits a faint glow. This radiation originates from diverse sources, including distant active galactic nuclei, hot gas within galaxy clusters, and various high-energy processes within our own Milky Way. The gamma-ray background primarily stems from interactions between cosmic rays and the interstellar medium, along with the interstellar radiation field. When high-energy protons collide with interstellar matter, they produce pions, which subsequently decay, emitting gamma rays. Simultaneously, inverse Compton scattering of high-energy electrons in the interstellar radiation field also contributes to the gamma-ray radiation. The X-ray background is more complex. It includes sources within the Milky Way, such as X-ray binaries, supernova remnants, and hot interstellar gas, along with contributions from beyond our galaxy, particularly active galactic nuclei and hot gas in galaxy clusters. The superposition of radiation from these diverse sources forms the sky background we observe across all wavelengths. Though these high-energy processes may seem distant, they are profoundly connected to our existence. Cosmic rays interacting with Earth's atmosphere produce secondary particles, some of which reach the ground. These particles present not only scientific research opportunities, but may also exert subtle influences on Earth's climate. More intriguingly, cosmic rays may have played a role in the origin of life. Some theories suggest these high-energy particles may have catalyzed the formation of organic molecules on early Earth, creating conditions conducive to life's emergence. In this sense, we share a profound connection with these energetic phenomena. Now, as your thoughts wander through the cosmos, feel these invisible energies and forces. Know that behind our tranquil night sky lies a dynamic universe teeming with vitality and change. Though these high-energy processes are intense, their existence enriches and fascinates our Milky Way. Let the tale of these cosmic energies lull you to sleep, knowing that in this universe brimming with unseen wonders, even the faintest forces shape our world and our Milky Way. This intricate system of matter and energy continues its story on the cosmic stage. Now, please close your eyes. Imagine yourself floating above the Milky Way. Surveying this vast spiral galaxy, you'll see hundreds of billions of stars orbiting their center in perfect order. Among them is an ordinary yellow star. Our Sun carries the entire solar system, on a journey through the Milky Way that spans hundreds of millions of years. The Sun lies approximately 27,000 light-years from the galactic center. This position is neither in the crowded galactic core, nor the desolate galactic outskirts, but rather in a relatively tranquil intermediate zone. Here, the Sun orbits the galactic center at a speed of about 230 kilometers per second. This velocity is so great that it would take only 1 minute to travel from Earth to the Moon. Yet, on the vast scale of the Milky Way, this is merely a leisurely journey. For the Sun to complete one full orbit around the galaxy takes approximately 225 million years. This time span is known as a galactic year, not a calendar unit, but a cosmic clock set for the Milky Way. To the ticking of this cosmic clock, Earth witnesses profound transformations unfold. Let us revisit the previous galactic year. Earth had just entered the late Triassic period. The earliest dinosaurs began appearing on the planet. Pangaea had not yet fully fragmented. The climate was warm and arid. Over the subsequent 225 million years, dinosaurs rose and fell. Mammals emerged from the shadows. Continental plates drifted apart, shaping the world we recognize today. When we compare Earth's geological record against the rhythm of the galactic year, we discover thought-provoking correlations. Major mass extinction events on Earth appear to exhibit a certain periodicity, with some cycles aligning with the timescale of the galactic year. This may not be mere coincidence. One possible explanation is that, as the solar system orbits the Milky Way, periodically traverses spiral arm regions, where stellar density is higher, and the interstellar environment is more complex. These periodic environmental shifts may influence the flux of cosmic rays reaching Earth, and subsequently affect the planet's climate through mechanisms like cloud cover variations, ultimately manifesting in shifts of biological diversity. Beyond its circular motion within the galactic disk plane, the Sun undergoes another movement, a vertical oscillation, much like a carousel horse, which rotates around its center, while simultaneously rising and falling. With a cycle of approximately 60 million years, the Sun oscillates up and down within the galactic disk, with a maximum deviation of up to 200 light-years. The cause of this vertical oscillation stems from the unevenness of the Milky Way's gravitational field. The distribution of stars within the galactic disk is not perfectly smooth. The uneven distribution of spiral arm star clusters and dark matter jointly shapes this gravitational environment. As the Sun traverses different regions of the galactic disk, the gravitational forces acting upon it undergo subtle changes, driving this vertical oscillatory motion. This vertical motion may profoundly impact the solar system. When the Sun moves away from the galactic plane, Earth may be exposed to stronger cosmic rays. These high-energy particles originating from intergalactic space are partially blocked by interstellar medium as they traverse the disk. Above the galactic plane, this shielding effect weakens. Some scientists speculate that these periodic fluctuations in cosmic ray flux may indirectly regulate Earth's climate by influencing atmospheric ionization and cloud formation. While this theory requires further evidence, it offers a cosmic-scale perspective for understanding Earth's long-term climate shifts. More intriguingly, the Sun's motion within the Milky Way is not isolated. It carries the entire solar system along with it, including all planets, asteroids, and comets. As the Sun traverses the galactic disk, the orbits of comets in the Oort cloud may become disturbed, causing more comets to enter the inner solar system. This could potentially correlate with impact events in Earth's history. Our understanding of the Sun's orbital parameters continues to deepen, precise measurements from the Gaia Space Telescope are refining our grasp of the sun's velocity and orbital shape. The latest data suggests the sun's orbit may be more complex than previously thought, featuring finer oscillations and perturbations. These perturbations stem partly from gravitational influences of other celestial bodies in the Milky Way, such as passing star clusters or dark matter halos, acting like eddies in a river, affecting the course of the sun's small vessel. Though negligible over short timescales, these effects significantly alter the sun's orbital parameters over millions of years or longer. Looking ahead, the sun will continue orbiting the Milky Way for billions of years. Yet, as the Milky Way gradually approaches the Andromeda Galaxy, the sun's orbit will undergo significant changes. In the gravitational dance between the two galaxies, the sun may be flung into more peripheral regions, or drawn deep into the newly formed elliptical galaxy. Within this grand cosmic clock, the emergence of human civilization occurred merely within the last second. Since the conclusion of the previous galactic year, all our history, all our civilizations, all our achievements unfolded within a single instant of a galactic year. This realization makes us feel both insignificant and acutely aware of life's preciousness. Earth's position in the universe lies not only within the habitable zone suitable for life, but also in a relatively tranquil region of the Milky Way. This region shields us from the intense radiation at the galactic core, while providing ample heavy elements essential for forming planets and sustaining life. This balance may not be coincidence, but rather a necessary condition for life to emerge in the cosmos and endure long enough to thrive. Now, as your thoughts journey with the sun through the Milky Way, feel the grandeur of this billion-year voyage. Every seasonal shift on Earth, every cycle of life's reproduction and evolution, unfolds against this vast cosmic backdrop. We are children of the Milky Way. Our existence is profoundly intertwined with the rhythms of this galaxy. Let this realization bring you peace, knowing we are part of a greater whole. Though our lives are fleeting, the cosmic story we belong to has been unfolding for billions of years and will continue to unfold. Within this vast scale of time, every breath, every heartbeat is an expression of the universe's rhythm. As the sun continues its voyage through the Milky Way, carrying us across interstellar space, you may relax with confidence, knowing that within this vast cosmic clock, this very moment is your moment. Let the slow rhythm of the galactic year soothe your thoughts and guide you into peaceful dreams. Now, let all thoughts slowly settle, like dust in starlight, gently drifting down in beams of light. No longer chasing, no longer clinging. Release the day's busyness. Let go of tomorrow's plans. In this moment, only existence, only breath. You are a child of the cosmos, traveling through this sea of stars. Now, you may rest assured, returning home. Let the Milky Way's arms embrace you. Let starlight's tenderness envelop you. Your very existence is a miracle. Billions of years of cosmic evolution have forged this being capable of thought, capable of feeling, capable of love. You exist safely at this point in time and space, gently protected by the laws of physics, embraced by the vastness of the cosmos. Nothing to worry about, nothing to fear. Let your body relax completely, from crown to toe. Every muscle, every cell, unfurls under starlight's embrace. Feel the bed's support, just as Earth holds you, while Earth orbits through space. The solar system drifts through the Milky Way. All is orderly, all is just right. Within this grand order, your rest is part of the cosmic rhythm. Just as stars need slumber, and galaxies need rotation, You too must sink into dreams. Let consciousness fade gently, like starlight merging into the night sky. No need to cling to wakefulness. No need to maintain control. Surrender yourself to a greater wisdom, to the universe's own design. Good night, dear traveler of the starry seas. May you continue your galactic journey in dreams. May you become one with the cosmos in your rest. When you awaken, you will carry the power of the stars and the blessings of the universe. Tonight, the entire Milky Way guards your peaceful slumber. Billions of stars adorn your dreams with their light. You are never alone, forever connected. Good night. May starlight gently caress your dreams. May the universe's tranquility fill your soul. Good night.